we'd like to talk to you about this idea that we had over dinner once while we were working on another subsea upgrade. And the more we thought about it, we realized it was actually not as crazy as what we initially thought. Where's this one? This one is next. Yeah. So let's go back in time a little bit. Who can remember what happened in February 2024? It's affected most people in this room. Yeah. There was a major subsea break in the Red Sea, and that was a major disruption to internet traffic. What actually happened was that there was rockets or missile attack on ships, and a bulk carrier was hit by rockets, which basically damaged the hull and the anchor. The vessel was eventually abandoned, and it floated around with the anchor dragging on the seabed. And it basically is probably the worst place where this could have happened, is in the Red Sea. The density of subsea cables in that area is actually, I think at the moment there's 16 or 17 active cables running through that region. And just those are the cables that were affected. Now, what was the impact? Network operators lost a lot of their capacity. Businesses all of a sudden didn't have access to their email system. Their cloud platforms was not available. Schools, if you think about schools, they have a lot of online platforms these days. That was affected. So basically every single internet user. And the main problem was latency. So if you go from the east coast of Africa to Europe, your latency under normal operations is about 107 milliseconds. If you have to reroute down from Kenya to South Africa terrestrial, and then up on a west coast cable, your total on a best case scenario is about 180. That all depends on which other subsea cable systems you're on which other terrestrial routes you go across South Africa. So the impact is quite severe. And then the other impact is cost. Providers had to then all of a sudden buy emergency restoration capacity. Across the South African backbones as well as on the West Coast subsea cables. Here we go. Engineering time. When something like this happens, I can assure you the engineers almost don't sleep. And trust, you lose trust from your customers. And quite a big one is the OEM supply chain, because of the emergency restoration capacity, it puts a lot of pressure on the OEMs because they have to provide the hardware for that restoration capacity. But now, what if there was an alternative? What if you can build a terrestrial route from the east coast to the west coast of Africa? That would solve the latency issue. It'll give you a shorter path to connect to the West Coast cable systems. And it will take strain off all the South African networks. If you think about it, when that break happened in the Red Sea, it's multiple terabits of capacity that have to be rerouted through other networks that wasn't really planned for. So why has this not been done before? Okay, there's a number of reasons for that. To build a terrestrial fiber route, you need reliable power all the way along the route. You need to power your repeaters or your amplifier sites. you also need civil infrastructure. You need repeater huts, you need ducts and sleeves. Every 50 to 150 kilometers, more or less. The ideal distance is probably around 80 kilometers between your repeaters, but you are largely dictated to where you build repeaters by where you can find infrastructure. So another reason is political stability and security in the region. There are civil wars ongoing. But then what if we can use subsea technology to overcome those barriers, the technical issues? Subsea systems is running for 15,000 kilometers plus. I mean, there are cables today that are 45,000 kilometers. So that it can certainly be done. Your repeaters are being powered from power feeding equipment from your cable stations. So there's not, you don't need reliable power along the route. The OSNR is an added benefit if you're using subsea cables to that. We will circle back to that a little bit later when we dive a little bit deeper to show you the benefits of that. And it is tried and tested technology. I mean, like, we've been doing it now for many, many years. So subsea cable systems basically solves all the technical problems that I mentioned before. Your reliable power infrastructure and your infrastructure, your civil infrastructure. And like I said, the PFE will power the repeater sites, and there's no need for civil infrastructure because the repeaters will be in subsea-like housings that is built for to lie underwater. Now, Ephraim is going to talk about the key components, seeing as he's from the OEM side.
Yeah. Thanks, Nick. Yeah. So, yeah, really, we have been, and Nick and I are not the only ones that have been talking about this for a while. You know, it is a fairly long-standing idea. Utilize subsea technology to enable terrestrial build-outs at speed. You know, and especially challenging environments where you know, like vast regions in Africa where there is no need for infrastructure. You know, you just need the road. In the Middle East, in other jungles, you know, places where there is no conurbations for miles and miles in between. The incident that Nick referred to, I have worked with all the operators in South Africa, turning up capacity on the West Coast, and it was really, everything was urgent, and as Nick says, there was very little sleep going on, and on top of that, we had the challenge of fighting internally, you know, to secure equipment to, you know, from projects that were being rolled out in other parts of the world. You know, just take it and bring it to Africa to restore that capacity. But really, it's also about, you know, rolling out networks at speed, you know, and at low cost. So, as Nick mentioned earlier, subsea technology is very mature. You know, it has very unique challenges. You know, you're deploying cables under the water. So it's really tested and proven. It is always at the leading edge of you know, optical transmission developments. And so the idea of reusing that know-how for terrestrial, it's not novel, but I think it's really important to take it seriously because we don't have the challenges, you know, that we would have in subsea. You'd need to mobilize a ship at $1 million a day. You know, every day that is traveling to 30 days to the cable cut, and then you know, repairing it. Nick and I can sit in a 4x4 and drive to a place somewhere in the jungle or someone else, and make that repair. So the challenges are not as stringent as sorry, I'll go back to that one. Yeah. So the key components: ILA, line amplifiers, repeaters. The requirement would be to mimic subsea behavior, which means working in a constant power mode. It does bring a series of benefits, the self-healing benefits, whereby, if there is a pump failure, you have pump sharing and so on. But at the same time, as I mentioned earlier, it will be much easier to drive to a place, although it's remote, rather than, if it's so I'll build this slide out and then talk to it. So there are several scenarios. Currently, we have many links, and I deal with those day in, day out, whereby a customer has a 300-kilometer link, and for when it was designed, it did the job. You could transmit 300 kilometers, one, say, 10 gig signal. You didn't need all the infrastructure in between, and it did the job for the utility or whatever that was using it. So the idea is that you can retrofit those links, by deploying a strand of copper or aluminum, which is actually important in terms of making it less attractive to vandalism. Hardened EDFAs that can work in constant power mode. We actually have in what was in Finera Nokia portfolio already a hardened amplifier that can be deployed in hostile environments, and I mean environmentally hostile. No cooling required, IP65 housing, and so on. Furthermore, you can obviously, with a little bit of effort, we can develop hybrid Raman EDFAs, which would then obviously enable the distance between ILAs, to be much greater, and develop the amplifiers for hardened housing.
Don't know what's going on.
Power feeding is also a very important consideration. The technology is very mature in terms of power feeding subsea cables. The same can be adapted and made modular in terms of scaling, if you like the requirement. You may start with one amplifier chain, and then you scale the next PFE to power the next one, for example, or you can have one PFE that could power multiple amplifier chain, multi-rail amplifier chains at the same time. Obviously, PFEs will be deployed at the ends of the line. Naturally, if there is you've got, let's say, 500 and 500 kilometer links in the middle, there is infrastructure. The PFE can be designed such that you make use of the one in the middle, for example. And this is all kind of pertaining to more or less off-the-shelf components that can be reused right now, to kind of start implementing this. The cables, the power optical cables are already actually, made. They are in existence, and which means this could be done right away. So there is power cables which like the one manufactured by Conscope and other suppliers, which have copper and fiber at the same time, fabricated. Do you want to take this?
Okay.
Yeah.
It's a good fit for all. Because these cables are designed to lie on the seabed, it's perfect for rainforests and wetlands. There will obviously have to be done some route planning done, and you will have to decide if you want to anchor it onto rocks, or if you want to run it through fast-flowing rivers like the Congo. There should be GPS trackers in every second or third repeater so that you can find the cable again. Like Afra mentioned, it will enable you to roll out these network infrastructure at speed. It can also be a good fit for deserts, where there's large deserts like the Sahara. There you have some other challenges. The dunes obviously move as the wind blows. So we would recommend that you will bury that just below the dune migration layer so that the dunes move over the cable and not with the cable. Again, also the GPS trackers. And yeah, then the local communities. There can be so much benefit for the local communities as well. Like Afra mentioned, if you do happen to come across a site on this route where there is reliable power infrastructure and you can build a repeater hut, then you can take one fiber pair and give internet access to the local communities. That is just one added benefit. This is just a slide that we show like how the PFEs work. So you'll see that these are your PFE equipments and these are your repeater sites. And you can power multiple fiber pairs with the same PFE. We reckon that for a 2,000 kilometer link, you will need about 3,000 volts DC power to repower multiple fiber pairs for that. Then I said we'll come back to the OSNR because there's actually quite a big benefit here. We modeled 2 fiber routes over 2,000 kilometers. The one was a subsea-like link where your repeater spacings is exactly 80 kilometers apart, and we use 0.2 dB loss per kilometer. That equates to 16 dB loss per span. And if you work out the OSNR, you end up with an OSNR of 23.58 dB. Now, if you take the same distance, and your repeaters are randomly spaced from 50 to 150 kilometers, like you typically would get on a terrestrial link, your OSNR drops to 21.87. That doesn't sound like a lot, but it is quite a bit. That can be the difference of you running 400 gig on a line rate versus 200 or 300 gig on a line rate. So your overall system capacity will be a lot higher if your repeaters are evenly spaced. Okay, we're not going to go too deep into the formula. I just wanted to highlight the OSNR calculation because that is the same for subsea as well as for the terrestrial. You've got your OSNR and dB there equals 10 log base 10 of your signal power over your noise that you get from your SLTE or your terminal equipment, plus the sum of every single span. And that is the OSNR. So why is equal spacing important? We touched on that briefly. Longer spans require higher amplifier gain, and that adds to the noise. Shorter spans require lower, so that will add less noise, but the sweet spot is evenly spaced repeaters. There you get the best performance over the end-to-end link. This is just a graph that basically shows how your OSNR drops over distance. And the reason for that is through every repeater, it boosts the signal, but it also boosts the noise. So it adds to the noise table. And obviously, the longer the link, the higher your noise table gets, to the point where you basically have to regenerate the signal. So that is done by having back-to-back transponders, and then it regenerates the signal and sends it back into the repeated link. Why that is not a good idea is because it's expensive. So just by doing that, you're doubling the cost of your capacity on the route. Okay. Then these are just some added benefits if you are going to start using subsea technology over terrestrial systems. For example, what we have there is a branching unit. Most fiber cuts on subsea systems happen in the shallow waters because of anchor drags, shipping vessels, and things like that. So we see that in the future there's going to be branching units with optical splitters where you will connect the subsea cable to 2 cable stations and to 2 different data centers, so that if you have a cut on the one side, it can switch to the other side.
So if
Yeah,
I may,
please.
in the industry, the cable manufacturers like ASN, Subcom, and the big guys, they are already talking about designing such cables whereby you have a branching unit which is a full fiber switch. And this is only when you come to the shallows. As Nick said, about 99% of the fiber cuts are in the shallows. You know, in the depths, it really rarely ever occurs. And so to all intents and purposes, here you have almost a redundant fiber route, including the subsea, knowing that in the depths, it is actually only one cable. So when in the shallows you have a cut, as we've kind of highlighted there with the crosses, then you fully switch. So one CLS is geographically diverse to the other one, and therefore your traffic is restored, and it's restored within minutes, hours, as opposed to days and weeks and months. And there is a cable which is already actually designed to do exactly this, to provide geographical redundancy over a much larger scale, and it is currently in deployment. So this is kind of already happening. So then this is a unified, if you like, end-to-end architecture. From the user perspective, it really is just a telecom network that's providing connectivity from POP A to POP B, and everything else in between, is just a cloud as far as you're concerned. And then you also have in terrestrial, we always design redundant links and survivable networks. So then you kind of end up with an architecture that provides with the high service availability across the whole network, including the subsea. Sorry, Nick.
Okay. So running up, is it ambitious? Yes, it is. Yeah. But is it impossible? We certainly don't think so. We think with the right approach, it can certainly be done. And that is it. So it's time for questions. Any questions?
I think we need to go and find that money man.
Yes.
Yes, please.
Good day, everyone. My name is Eric. Just one question. Can you explain to me the back-to-back transponder?
Okay. So when your OSNR drops to a certain point where your receiving transponder cannot read the signal anymore, you're going to run bit errors, and your customers are going to complain. So one of two ways that you can do to fix that is you have to clean up the fiber so that your OSNR drop is less, or you have to regenerate the signal. So then what you do is you have another set of transponders. So then you put a transponder there. And then you have another transponder where you basically connect your client ports back to back. And then you have, so you're basically cutting your link in two. In an ideal scenario, you would have one transponder at pop A and one transponder at pop B. And if you have to regenerate it, you will have to have a set in the middle as well. So that basically doubles your transponder cost for your capacity on that link.
Yeah.
Okay.
Hey, Mark.
Mark.
Hi, Mark Tinker, Transmission Co. Thanks, Nick and Afrim. This is fantastic. I suppose the question from my side would be around the, let's say, the Sahara build.
Yeah.
What would be the plan there to manage thermals for the I'm guessing you're using the same casing as you would in subsea.
Yeah.
So how would you manage thermals for that in that
Yeah.
situation, both night and day?
So yeah, thanks, Mark. So Nick and I actually have looked into different environments, and in the desert, surprisingly, below a certain depth, certainly when you go below the dune migration layer, the temperatures are actually much, much lower than at the surface. So it is a very suitable, if you like, environment on doing that. So yeah, it's by burying it beyond 1.8 meters, I think naturally it is cool. And for those environments, we would need to build a subsea-like repeater, with multiple repeaters, multiple pumps, and the appropriate PFE, and then yeah, you would do that. Yeah.
And also the repeaters that is proposed for this kind of solution is built to operate in minus 40 to plus 60 degrees Celsius. So, yeah.
And again, to address the question, Mark, we are currently actually working on a project which is Trans-Sahara in the Middle East, where we're building. We've got a solar solution in order to break that link. But the biggest challenge, because the amplifiers, they really consume little power. With 250 watts will amplify bidirectionally your whole C-band. The biggest challenge is the aircon, to enable it to work in that environment. So, the biggest power consumption. So.
Okay.
Hello.
Hi.
It's Ronald from Nepean. I think I might have a stupid question, but I'm going to ask it in any case. So when they put the cable in in subsea, they've got a huge big ship with a huge hole.
Yep.
How are you going to actually do that type of thing on land? Because you're not going to get a truck that size. I mean,
No.
how are you going to effectively do it so that you can actually lay it properly?
Yeah, no, look, that it will have to be specialized deployment vessels that will probably still have to be developed for that. And that will also largely depend on the terrain you're going through, because it should be a different type of deployment vessel if it's through a swamp or if it's on a desert, for example.
Yeah.
So.
So yeah, I agree. So it is completely different environment. Another level of kind of study that Nick and I have done is a modular solution. If it is a subsea-like cable which will cater, end to end, the distances vary. It can be anything between 200 and 2,000 kilometers. So we would do a modular drum, and then deploy it as normal terrestrial deployment. It will be a bit thicker in terms of armoring, as and where needed. But yeah, it's modular, and you can do, for example, 100-kilometer length or 200, whatever it is. and then splice and then carry on.
Okay.
Thank you.
Thank you.
Gentlemen, thank you so much for joining us. Afram and Nick, thank you.
I see a gold bar in there. Thank you.
And with that, we bring the session to a close. Thank you to our speakers and all of you for being such great audience. We now invite you to join us for lunch.